I'd like to continue the idea that we were discussing earlier, which was for the ionic compounds. In the last case, we had produced the structure for aluminum sulfate, and again, just repeat this. Aluminum sulfate can be written with the structure expressed as Al subscript 2 with the parentheses SO4 parentheses close subscript 3, and this presents the configuration for aluminum sulfate. Now, the ionic compounds also have a situation in which they can be produced in the presence of water. And in that case, what happens is the water molecules become entrapped inside the structure in a very specific way with respect to the crystal structure of the various compounds that are ionic. For example, calcium sulfate, which to go through in the same sense that we had for aluminum sulfate, calcium sulfate can be written with structure again of calcium as a +2 in this case. Sulfate, of course, just as you saw, is a -2. So these balance out very conveniently. So we have calcium sulfate as CaSO4. Now, turns out that if we prepare calcium sulfate, or it is occurring naturally in the presence of water, then what happens is we form hydrates. Now, hydrates, as I mentioned, require the addition of a water molecule as part of the configuration for the ionic compound. It may require more than one molecule per what is known as a unit cell. But in the case of calcium sulfate, this particular material can form a hydrate, which is calcium sulfate, and we write that with a dot, and then we can say how many molecules of water are contained within a unit molecule of a unit formula of calcium sulfate. In this case, we have, for each structural component of calcium sulfate, we have 5 water molecules. So how do we go about naming this? Well, in this case, what we're going to do is we're going to resort to the application of Greek prefixes. You may recall those are presented as one would be mono, which is typically not used. 2 would be di. 3 would be tri. 4 is tetra. 5 is penta. 6 is hexa. 7 is hepta. 8 is octa. 9 is nona. Now you can change to ina, but we'll stick with nona for now. And 10 is deca. There are, of course, more. There's undeca, dodeca, etc., but for our purposes, up to 10 is enough. So we could have some compound, and it would be an ionic form in this case, that would incorporate any and of these particular structures with water. So here's an example of a compound. We're going to write, let's do this down here. I'm going to have compound ionic, compound Na2, SO4, a dot 10, H2O. So this would be named as sodium. So we have this here. Sulfate. It's here. And this is deca. for tin, and this is hydrate. So altogether we'd have sodium sulfate decahydrate as an example of a hydrated ionic compound. Another example of a hydrated compound might be what's found in Epsom salts. Epsom salt is chemically a compound of magnesium, and this is magnesium, which has a +2 charge, sulfate, which has a -2 charge, and we have water. In fact, we have 7 molecules of water for each formula unit of magnesium sulfate. So we would have Mg SO4 dot 7 H2O, and we would name that magnesium sulfate, and in this case heptahydrate. As you can see, we are still using the same general format as we have for the others. And this gives us a way to express hydrated structures of ionic compounds. There are many other examples of hydrated ionic compounds. So if we wanted to distinguish, in some cases, the application of hydrate versus the compound that doesn't have water attached to it, we might have to emphasize that fact. So if we had something like magnesium here, if we took the magnesium sulfate heptahydrate and we heated it, what would happen is we would end up with magnesium sulfate here, solid. These are solids, by the way. And the 7 water molecules would end up being removed as gas. And of course, eventually that would become a liquid. So we would have a partial decomposition here. Now, in order to distinguish this, we might want to emphasize that this would be named anhydrous. Anhydrous. Anhydrous magnesium sulfate. This may be necessary to emphasize the fact that we had started with something which was hydrate, magnesium sulfate heptahydrate, and we were able to warm it gently and produce anhydrous magnesium sulfate. Not all ionic compounds need to be expressed as anhydrous, but you may want to do so when the ionic compound has been undergoing a change from a hydrated form to the anhydrous form. So this, of course, is hydrated form. And that process gives us a way to discuss the conditions for ionic compounds as their structure includes or eliminates the application of water molecules in their three-dimensional crystal structure.